Hi, Math 95. So I wanted to go over the parts of chapter 9 that we did not do in class last time. So what I'm going to do first is one video that just has the actual the sections that we did, but just the examples that we didn't do. And then I'll do a second video with the rest of the notes. So let me just remind you, we kind of started out, we're talking about factoring. We started out with these first couple pages where we talked about listing all the factors, all the common factors, and then the greatest common factor. Also finding the greatest common factor when we have two um, expressions that both have just variables. Okay, so we said, well, if we're looking to see what we can take out of each one, yes, we can take an x out of each one. Yes, we can take an x squared, no more than that, because then this one runs out of x's, right? So the greatest common factor here would be x squared. And sort of the rule here is that the greatest common factor is going to be the variable with the smallest exponent on it, because that's the one that's going to run out first. All right. Then we did some examples of finding two numbers that multiply to something and add to something else. And so this kind of seems like it's not really connected maybe, but we did a bunch of these. And then we got into factoring polynomials. So we started out by factoring out the greatest common factor, the GCF, thinking about both the numbers and the variables for those. And then in the parentheses, we write out whatever we have left from every term when we have factored out that GCF. If we want to check those, we can multiply the outside part, the GCF, by everything inside. So we have a couple of these that I left for you to try. So I'm going to go over them now. You can check your answers. And the answers are also on the completed notes in Lumen as well. So if we look at this, we have, let me change to red. Okay, so we have three terms here. So we need to figure out what the GCF is going to be. So we look at the numbers 25, 30, and -15. We want to think about what those have in common, the biggest thing they have in common. If you're not sure, you can write out the factors to any or all of those numbers as we did here, and then you have to find a factor that goes into all of them, the biggest one. So I know that 5 goes into all of these, and in fact, it is the biggest factor that goes into all of them. So my GCF is going to have a 5. If I look at the x's and the y's, I know that I want the smallest variable that's in either of those. So x's, I have x to the third, x to the second, x to the first. That means x to the first is part of my GCF. It's the most x's I can pull out of all three of those. And y, we have y to the fourth, y to the fifth, and y to the third. So y to the third. Okay. Now, in parentheses, I need to have three terms. Each of these terms, I'm going to have in here what's left when I factor out or divide out this GCF. So 25 divided by 5 is 5. X cubed divided by x, think about quotient rule, subtracting those exponents, that'll be x squared. And then y to the fourth divided by y to the third is just y. If it helps you to write it out as a division problem like we did in chapter 7, that's perfectly fine. Okay, then you can see how each of these works with that quotient rule. Next, I'm going to have 30 divided by 5 is 6. X squared divided by x is x. Y to the fifth divided by y to the third, again, quotient rule, so 5 minus 3 is going to be 2. And you can picture what we talked about when we first started those exponent rules, 5 y's, 3 y's in the bottom, we cancel them out, we have that y squared on top. Finally, 15 divided by 5 is going to give me 3. Now x divided by x cancels out, y cubed divided by y cubed cancels out. So I just have this as my answer. If I want to check it, which is always a good idea, I can take this outside term and multiply it by each of the inside terms. Okay, so let's look at number 5. When I look at 15 and 3, my GCF is going to be 3, and then x and y to the first power. If you're not sure exactly how come that would be our GCF, you can pause the video, kind of think it through for a minute. 15 divided by 3 is 5. X cubed divided by x is x squared. Y squared divided by y is y. 3xy times 5x squared. Oops. That was missing something, isn't it? I got so caught up in thinking about what I was doing that I missed part of it. Okay, so the reason I have this one is because I have this and then I have another term. So I have to have another term here to make up for this one. Well, we kind of did it up here, but 3xy divided by 3xy is going to be plus 1. So don't do what I did at first. Forget that. And if you check your answers, you will catch that kind of mistake right away. Because if you check it, this times this gives you the 15x cubed y squared, but then I need this 3xy times 1 to give me the 3xy. Okay, so let's move on to where else? All right, so we talked about factoring easier trinomials. We did a few of them, and then we kind of skipped down to some of the harder ones down here. Okay, so in some of these, I might have done in one class and not the other. So if I did it in your class and I'm kind of redoing it now, that's okay, it's a little extra practice, right? Okay. Let's finish erasing this part. All right, so remember that when I'm, excuse me, when I'm doing this, I need two numbers that multiply to the number on the end and add up to the number in the beginning. And that's what's going to go in my parentheses. So x times x is going to give me x squared. That's the easy part. But those two numbers at the end have to multiply to this number and add up to this number. So in this case, we're looking to multiply to negative 24 and add up to 5. So remember we start out with numbers that are going to make this part true. Okay, so I'm going to think about factors of 24. 1 times 24, 2 times 12, 3 times 8, 4 times 6. Now I need it to be a negative 24. So I'm going to have in each pair one number positive and one number negative. This tells me that since those have different signs, there need to be more positives if it's going to add up to a positive number. So the smaller number in each case needs to be the negative. So if I look now for a pair that's going to add to 5, this is going to add to 23, this would add to 10, this would add to 5, and negative 4 and 6 would add to 2. So I want negative 3 and positive 8 in either order, as long as the 3 is negative and the 8 is positive. So I could have x plus 8 and x minus 3, and that's fine. Remember to check this, which you always want to do, because this kind of problem is very easy to check. So you want to make sure you're doing that. You can just multiply it back. So I have x minus 3 times x plus 8. I would have x times x is x squared. X times 8 is 8x minus 3x minus 24. X squared plus 5x minus 24. I check and see, is that what I started out with? Yes. And I mentioned this in class, but most often this is going to be right because it's x times x, and this is going to be right generally because you chose numbers that made that true. It's this middle one. If there's a problem, it's generally with the middle number, because maybe you switch the signs and so it'd be -5 instead of positive, or you pick the wrong pair or whatever. So really be careful about that. Okay, let's look at the next one. So x squared plus 10x minus 24. So I, again, need two things that are going to multiply to negative 24. I can actually look over here because, again, I want them to add up to a positive. So the bigger number in each pair is going to be positive. So if I look at this now, add up to positive 10, this is going to be the one I want there. So I'm going to have x minus 2 and x plus 12. Okay, again, I want you to check your answer every single time. Even if you don't write out a check, do it in your head. So x times x is x squared plus 12x minus 2x and then minus 24. Well, 12 minus 2 is 10. Okay, so next one. This looks very similar, right? All three of these the numbers look very, very similar. I had, well, especially these two, plus 10 minus 24, plus 10 plus 24. So think about what that means. Well, when I'm thinking about factors of 24 now, I have the same numbers, 2 and 12, 3 and 8, 4 and 6. I need to have a positive number. So that means that my signs have to be the same, either positive times positive or negative times negative. Well, when I look over here, if they were two negatives, they would never add up to a positive 10. So that means they must both be positive. So I can just leave them like this. Again, I look through to see which pair, these all multiply to 24, which pair also adds up to 10. Well, it's this one. So it's going to be x plus 4, x plus 6. Okay, so let's go on. Now, difference of perfect squares, I started in one of the classes, but I didn't really get very far because we were running out of time, and I don't think I even started it in the other class. So I'm going to not subtract, I'm going to erase all this and start over for both classes with the difference of perfect squares. So let me just erase this here. And we'll look at this type of factoring. And then once we get this little section done, I'll stop this video. And the next video will do stuff that we didn't start in either class. Okay, so some other kinds of factoring. All right, so when we're looking at this, factoring the difference of perfect squares. Okay, so as I wrote up there, difference means subtraction. So I'm going to be doing this when I have a problem that has subtraction and the two things being subtracted are both perfect squares. Okay, things like x squared, x to the fourth, or things like 81, 49, 25, right? Anything that's a perfect square. So let's start though kind of backwards like we did before by thinking about the multiplication part and how we get to the thing that we'd factor. So I have these two binomials, x plus 3, x minus 3, and I want to multiply them. So x times x is x squared. X times negative 3 is negative 3x. 3 times x is 3x. 3 times negative 3 is minus 9. Okay, so pretty basic like we've done a million times. Now, when we go to combine like terms, these two are my like terms, plus 3x minus 3x. Well, when I add those two, they cancel out and they become 0. So what I am ending up with here is x squared minus 9, because this is minus right here. Okay, so that's what I get when I multiply these two binomials. Now, normally when we multiply binomials, these two combine into something, not 0. So I would end up with, x squared plus 5x minus 9 or something like that. Well, here I only have two terms. It's kind of unusual. We were thinking about our trinomials as being in this form. Well, I'm missing this term, right? So here's where I have to pay attention to this being the difference of perfect squares. So difference means subtraction. I'm subtracting two things that are both perfect squares. So when we have a situation where we're being asked to factor something, it only has two terms, I want to see if it is the difference of perfect squares, because if so, it tells me how to factor it in a certain way. A special way so that that middle term cancels out and I have no x term there. So let's look at this one. If we have x squared minus 100. So first of all, I want to think, okay, is this a perfect square or difference of perfect squares? And yes, it is, because it has two terms. I'm subtracting them. X squared is a perfect square. 100 is a perfect square. Okay. Remember, for variable terms, it's a perfect square if the exponent is divisible by 2. So I have that set up here. So what I'm going to do is I'm going to factor it into two binomials. And the way this works is that the square root of the first term here, the square root is the first term in each binomial. And then the square root of the second term is the second term of each binomial. Okay, so my square root of x squared is going to be x, and that goes here and here. My square root of 100 is 10. That goes here and here. Well, in order to get this to be a negative and in order to get these two to cancel out, I have to have opposite signs, 1 plus and 1 minus. And that is how I'm going to factor something that's a difference of perfect squares. They're going to have binomial factors that look exactly the same except for the sign. If I check this, I would have x plus 10 times x minus 10. X times x is x squared. X times negative 10 is negative 10x. 10 times x is plus 10x. 10 times negative 10 is negative 100. So again, I can see that my middle terms are going to cancel out. I'm going to end up with x squared minus 100. Okay, so let's look at the next one. 9x squared minus 49. So I know that I need to make two binomials. Okay. The square root of this one will go here and here. The square root of this whole thing. So the square root of 9x squared, think about what we did with exponents and square roots and all that. Square root of 9 is 3. Square root of x squared is x, which makes sense because 3x times 3x is 9x squared. So 3x, that whole thing goes here and here. 49. Square root of 49 is 7. Plus and minus. Okay, again, if I check it, I'm going to get that 9x squared here. My inners and my outers are both a 7 times 3x, so I will get negative 21x plus 21x minus 49. 9x squared minus 49. All right, let's look at number 11. So number 11, if I look at that, I think, well, I might not know about 384 right off the top of my head, but I know that 6 is not a perfect square. So I might be, quick to say that's definitely not the difference of perfect squares, but we always have to check something first before we can say that. And what we have to check is whether or not there's a GCF, okay? Again, I didn't mention it here. I mean, there clearly isn't one here because there's no x here and there's no number other than 1 here. Here, since this is the difference of perfect squares, or this already is, they both are perfect squares, I could think about 9. I still would want to think about taking it out, but 9 can't go into 49. Okay, so I kind of skipped over that step a little bit here because I knew there wasn't a GCF and I wanted to get you used to the perfect square part. But really, we always need to look for a perfect square. So when I look at this one, if there's a number here that I want to get rid of, I mean, the nicest thing is if 6 goes into 384, then I can get rid of that whole 6 out in front. So if I divide that, then it is true that 6 goes into there. So I want to do the GCF first before I do anything else. So I have x squared minus, if I take 384 divided by 6, I get 64. Now, so here's what we're going to start doing when we have a problem. We're going to look for a GCF. If there's a GCF, we pull it out and write what's left in just that one step. Don't do anything else to it. Then we now have to start looking at what's in my parentheses. If it's something I know how to factor, I have to keep going. Here I have the difference of perfect squares. So 6 times x and x, that's my square root of x squared. Square root of 64 is 8, and I have a plus and a minus in some order. You could put minus and then plus. Remember how to multiply 3 things together. I can either multiply these two, get to here, multiply 6 by distributing it, get back to here, or I could multiply 6x plus 48, right? 6 distributed through there, multiply this by x minus 8, and I would still get the same thing. If you notice there's 48x here, minus 48x there. That's going to cancel out. Okay, next one, x to the 4th minus 81. Okay, again, x to the 4th is a perfect square because the exponent is divisible by 2. So square root of the first term goes here and here. Square root of x to the 4th is x squared. Square root of this guy goes here and here. Square root of 81 is 9. Plus and minus. Now, it's tempting to think I'm done. However, what you'll learn when you're doing factoring, you always have to be on the lookout for, is there another step I can do, okay? Sometimes a factoring problem will have 3 or 4 steps. Maybe I pull out a GCF, and then there's difference of perfect squares, and I can go a couple times, or you'll see as we get to more of these factoring methods. So if I look here, this one we can't do anything with. We'll talk about that in a minute. This one is the difference of perfect squares again. So I'm going to leave this first one as is. This one can get broken down again because it's the difference of perfect squares. So x and x, 9, so plus 3, because that's the square root of 9, and minus, oops, not 9 there, minus 3. Okay, so just to step back for a second, we did difference of perfect squares here. One of those factors is again itself the difference of perfect squares, so we have to break that one up. Okay, so I'd said, well, that first part, x squared plus 9, we weren't going to be able to do anything with it. So let's talk about that a little more. So x squared plus 9 looks an awful lot like what we've been talking about, but except for the fact that this is the sum, right? So can we factor either x squared plus 9 specifically, or really what we're asking is any sum of perfect squares? Can we factor that? Okay. And the answer there is going to be no. So why not? Well, let's think about this for a minute. If we have x plus 3 times x plus 3, x times x is x squared, plus 3x plus 3x, plus 9. These do not cancel out, so it actually is going to be x squared plus 6x plus 9. Okay. If I have x minus 3 times x minus 3, I would get x squared minus 3x plus 9. Again, these would not cancel out. I'd end up with this. What I'm trying to do is find two binomials that multiply to give me x squared, no x term, and then a plus 9. Well, the only way to have no x term is to have them cancel out here, like they do in a difference of perfect squares. If they cancel out, that means they have to have different signs. But if they have different signs here, it means they were different signs here, which would give us a minus 9, not a plus 9. Okay, so any sum of perfect squares is not factorable. Okay, so you're just gonna leave it, can't go any farther. Now, that's different, any sum of perfect squares. When you are in Math 120, if you go on to Math 120 next, you will see that if we can have a sum or a difference of perfect cubes. So for example, like I'll say x to the third minus 8, okay, because this could be x, this cube root of x cubed is x, the cube root of 8 is 2. So these are both perfect cubes. We could also have the sum of perfect cubes. Both of those are factorable. There's a formula that you'll get given and kind of plug into it. It's a little more complicated, but you can do that, okay? You do that later on. But you cannot do this for any perfect squares. All right, so that's where I'm going to stop in this video. The rest of the factoring I will do in another video because it's stuff that we didn't do in either of the classes. All right, thank you for watching this, and if you have any questions, let me know.